Okay, we're going to talk about a few things today. We're going to talk about Kepler's laws predominantly, but before we got to Kepler's laws, I wanted to make sure that I just briefly touched on this idea of heliocentrism versus geocentrism. So, geocentrism here is the belief Earth is the center of the universe, and it's what classically people believed, right? People believed for a long time, and there's various reasons why. There's some religious reasons to believe that we're the center of the universe. There's some obviously just ethnocentric reasons. People tend to think of themselves as sort of the main character themselves. The human race is sort of the main character of the universe, right? So we have these biases that are naturally going to make us think that we're kind of the center of the world, and it makes the sort of formal geocentric model was first proposed by Aristotle, very smart guy, and then finally it was refined by Ptolemy so that it matched a lot of observations. So I think we have this sort of issue where commonly, we think of people in the past and we think about oh man, they were dumb or they were stupid. I can't believe they have thought that. Why would they think that? That's such a primitive or silly thing to think. But when it comes down to it, there actually is a lot of observational evidence. There's a lot of evidence that would really support geocentrism. I mean, think about, the people who developed this were typically outdoors, their entire lives. So, what they saw every night was the same thing. They would see the stars going around the Earth. They would see the sun going around the Earth. I mean, that's what it looks like, right? Because we discussed previously how, you have this frame of reference, a moving frame of reference. So the from a physics perspective, saying that Earth is still and the sun moves around the Earth is sort of equivalent to saying that the sun is still and Earth goes around the sun. And again, those two things seem to be the same, but you don't really feel like you're moving, right? I don't feel like Earth is really moving. We feel like Earth is stable and still. It's natural to think of Earth as being in the center. So the idea was Earth was in the center here, and that's what you can see this model here. I know it's really small, but you have access to this PowerPoint. I should mention real fast, if you want to find the PowerPoint, you can find it under Materials, Classwork tab. It's just at the top, Kepler's laws. So I forgot you can see that there. Anyway, so Earth was in the middle, and then you had the moon was the closest sphere. You had these interlocking spheres. So the moon was closest, and then it was, I think, Venus maybe. I don't know. I can't. It's a small picture, but anyways, the idea is there's these circles where the different planets are, and then finally you have on the very outside the stars, and there's sort of this idea of the celestial sphere, this sort of fixed sphere where all the stars were, and it just spun around Earth. And again, it makes a lot of sense, right? If I ask you to give me a piece of evidence to show that actually Earth goes around the sun, you'd be hard pressed to do it. I couldn't do it. I can't come up with one single piece of evidence on my own without some very specialized equipment to show to say that the sun is in the center. But heliocentrism was eventually put forth. Of course, we know this is correct today. It's just the idea that the sun is in the center and all objects in our solar system go around the sun. It was first proposed by a guy named Copernicus. He didn't actually publish his theory till right before he died. A lot of people thought there was going to be some pushback. Galileo was one of the first people to find some evidence to support this theory. You may know that Galileo is credited with inventing the telescope. That's not exactly true. There were plenty of tools to look far away places, telescopes, but he was the first person to use it in astronomical observations. He was the first person to use it towards the sky at night. Most people used it, from ships in wartime, from towers in wartime. It was a piece of military equipment, potentially used in surveying as well. But anyways, Galileo is the first person to look at the different planets, and he saw that Jupiter had moons. Jupiter had these 4 little dots that went around it. And you can see this in pretty much any telescope today. If you have a telescope and you look at Jupiter, you'll point there and you will see there are little 4 bright dots around Jupiter, and they move around. Now, you can't see them moving real time, but you can observe them one night and then observe them in the next, and they'll be in different places. So he showed that there was there were moons that were going around Jupiter. And that immediately undermined geocentrism, because again, the idea behind geocentrism was everything goes around the Earth, and here was something clearly not going around the Earth. Kepler, we're going to talk about Kepler in a minute. Kepler also was able to support this idea of heliocentrism because of measurements that he made. They just didn't work out if you used the geocentric model, the Ptolemaic model. It just didn't work out. The measurements weren't quite there. So he eventually was in support of the heliocentric system. And since Kepler, and it made so much sense, most people adopted it. But the actual first piece of experimental proof that showed definitively that heliocentrism was, the way our galaxy, or I should say our solar system works, wasn't found until 1819, right? You had to have very specialized equipment. A guy named Bessel was able to measure stellar parallax. That's where the stars move because of your motion, right? So the apparent position of stars changes. But because the stars are so far away, it's incredibly hard to measure. And again, when it was a cutting edge technology in 1819 was able to measure that stellar parallax. But I just want to point out, and sort of to link to where we're getting to today, there's a lot of stuff we know today, and it's easy to assume like people were just wrong or stupid back then. But of course they weren't stupid. Very, very smart people back then, just like there are smart people today. They were limited by their technology. They were limited by what they could see, and so they obviously eventually settled on the heliocentrism. But again, for a long time, it was pretty close debate, and both sides had some positive things they could do. Okay, so today we're going to talk about Johannes Kepler. He is most famous for developing his laws of planetary motion. But before we talk about him, we get to talk about Tycho Brahe. Tycho Brahe is a very eccentric figure, a very interesting figure. He was extraordinarily wealthy, right? That's kind of weird already, right? We don't think of astronomers as being incredibly wealthy people, but he was incredibly wealthy. And if you start to think about it, you can probably piece together. I mean, think about what time he's living, right? He's living in the late 1500s, working in the late 1500s here. Astronomy was incredibly important back then. It was incredibly important because people needed to know what time it was. People needed to know what time of year it was. People needed to know when they could plant crops, when was the best time to get them back out, right? To sow and reap, these sort of things they needed to know. And so being able to have an observatory and make precise measurements allowed you to know what time it was. Today we take for granted the fact that we know all this time. So Tycho Brahe was obviously a very wealthy dude. He has a few eccentricities. You'll notice in this picture here, you might be able to tell his nose looks a little strange. He had a nose made out of silver because he got it shot off in a duel. He had a duel with somebody, his nose got shot off. So he made a different nose made out of silver. He also had a island observatory, you see there. And he would invite people over and throw kind of big parties. It's ambiguous whether it was like an elk or a stag or a moose, probably, or reindeer, probably most likely an elk. But he had an elk there that he would give lots of beer to, and they would drunkenly stumble around and crash into things. And then finally, one of his favorite pranks was he liked to have little people sit under the table, like hide under the table while people sat down to eat. And then during dinner, they would like kind of tickle their knees. They would come out and tickle your knees, and you wouldn't know there was a person there. And then you look down, and all of a sudden there's like a little person there. Pretty freaky stuff, but yeah, he's a weirdo. But he was brilliant, right? He had great tools. He could make the best measurements for the planets. So this was Kepler. He's from Austria. He was interested in how the planets move around the sun. So again, he wanted to know more about how the planets moved because he had some like cult-like beliefs about them. There were different. He thought that the planets corresponded to different platonic solids, and that there was this sort of mysticism to it, and there was this music of the universe. And if he could figure out, how the planets moved, he could figure out this like cosmic symphony, this cosmic harmony, this cosmic music, and then he could like use that to control the world and use magic and stuff. So kind of crazy. He had like certain religious ideas too. But regardless, he was brilliant. Again, you see a pattern here. And so he went to Tycho's Island to look at these measurements, to take some measurements for himself, so he could try to figure out how the planets were moving around the sun. First of all, let's be clear about what happens when we say planets. So when you look at the night star, you probably have seen planets in this night sky without knowing it, because they just look like stars. They don't look any different. I mean, some of them are brighter, right? So Jupiter's pretty bright. Venus is incredibly bright. But in general, they just kind of look like bright stars. However, if you go out night after night, you will notice that all of the stars maintain the same positions relative to each other, right? That's why we can have constellations, right? The constellation Scorpius has been the same forever, and, well, pretty much will be, at least in a human scale, will be the same. But and the other constellations stay the same, and they are always the same locations, right? So, for example, when I teach like a visual observational astronomy, one of the first things we do is we figure out how to find the North Star, Polaris, right? So that's the one that points north. Easiest way to find it is you find the Big Dipper, which is pretty easy. It's very distinct, very bright stars, and you use two stars to point to the Polaris, to point to the North Star. Those are called the pointing stars. And it's always the same, because even though the stars all rotate, they all rotate together. So they move together, which is why in this geocentric model, they had this sort of sphere, of the celestial sphere where the stars were. But that's not true for planets. And that's why we noticed them in the first place. That's why these people knew about planets. They didn't have incredible telescopes where they could get really cool pictures of Jupiter or really cool pictures of Saturn. That didn't happen. Even before they had telescopes, the Greeks knew about the planets because they would wander around. A Greek word is planetos. Planetos means wanderer. So these are moving around every night. So this is like a picture where they're taking the same portion of the sky every night. You'll notice these stars back here are not moving, but this star moves pretty much all the time. In fact, you actually get what's called retrograde motion here. We're not going to look at this link, this video here, but feel free to look at it on your own. It is interesting. But the point is that we knew about the planets, and we knew they were special because they would change position relative to the stars. And that's why people said, oh, they're on their own spheres. They're not on the celestial sphere. They're on their own sphere. And actually, the Ptolemaic system of geocentrism had these things called epicycles and epicenters to account for this retrograde motion. So one of the sort of philosophical ideas that you need to know that Aristotle pointed out is that they saw circles as the perfect shape, of course. So they assumed that all the planets moved around in circles because the planets were outside of Earth, right? So you know that there's like these, you've probably seen, if you've seen Avatar or Korra, or any, it gets used a lot. You know there are the four elements: earth, wind, fire, air. The four elements, that's Aristotle. The idea was there are four things that make up everything else. But there's actually more. There's another element. There's this stuff that's not for Earth, right? So the four elements are stuff that comprises things on Earth. Things that are corruptible, changeable, not perfect. But for perfect stuff, it was made out of something different. So the heavens, right? Literally, heaven was made out of this stuff called the aether, and the aether was a perfect circle. So if you were to ask Aristotle, right, say, hey, Aristotle, why do the planets move around in circles? He would say, oh, well, because the circles are perfect shape, and they're perfect, unchangeable objects out in space, in the heavens. That's what he would say. So that's what Kepler was going to try, right? So Kepler tried to use the circle to match the measurements that he got from Tycho Brahe, but it didn't work. He used Mars at first, which is why you see Mars here. It didn't work. But he did find that if he changed the shape just slightly, he could get the measurements to work out. Instead of a circle, if he made him into an ellipse. So real quick, if you forgot what an ellipse is, a circle is where every point on the circumference is equidistant from the center point. In an ellipse, it's not the same. An ellipse doesn't have one center point. It has 2 points we call foci. Just the plural, focus. So the two foci, when you have I think it shows on the next one, but the idea is that, if you see this point here, if I measure the distance from here to here and here to here, if I add up the sum of those two, it'll be the same no matter where you are. Let me see if I can draw that for you real quick. I didn't get this slide prep, so I can do it real quick maybe. Let's do it like this. All right. So what I'm trying to say is, I'm not going to be able to draw a straight line, but I'll try my best. Okay, so let's say we have there. Okay, so let's say we have sorry, I want to make my pen tip bigger. I guess I can't. Okay, whatever, it's fine. All right, so let's say we have this point here. Right? If I was going to measure its distance, you wouldn't measure from the center, you measure from the foci. So this distance plus that distance. And you would add those two things together. So let's say this was 10 and this was 15. You'd find the distance, the combined distance would be 25 to there. And then let's say we took a very different point, like this point right here. So if you measured this distance, you would have, let's see if I'd use a different color. Okay, so you'd measure this distance, and then you'd measure, this distance here. And what you'd find is like this distance is 5, and this distance was 20. So if you add those together, obviously you get 25. And I won't go any more examples, but you get the idea, right? So that's what makes an ellipse unique, is that you can pick any, you can pick any point, and the distance between the two foci will be the same. They'll always equal the same. Okay, so you see the problem here, though, because theologically, like an ellipse, that's not a perfect shape. Like a circle's a perfect shape, ellipses aren't perfect. So this was a problem for some people. But nonetheless, this is Kepler's first law. So Kepler's first law of planetary motion: planets move around the sun in ellipses with the sun at one of the foci. And he found that this was true for every planet he looked at, right? So if he went from Mars to Jupiter, he found that Jupiter also followed the same path. Neptune, I don't know if he knew about Neptune, honestly. He knew about Saturn. Saturn followed the same path. Mercury they didn't see a lot of, but I think they knew about. Venus followed it. So they found that every one of these planets matched up with this concept of moving in an ellipse. So there's some vocabulary here. So you see here, this is Mars, here's the sun, and here's the other foci. Now, I want to be clear how elliptical something is. We call it the eccentricity. So a circle has an eccentricity of 0. A circle is not an ellipse at all. A straight line, has an eccentricity of, 1. So your ellipse has these different eccentricities. I think it's found by taking the ratio between the major axis and the semi-major axis and the semi-minor axis. But I'm not 100% sure on that. We don't need to know that. But my point is that these are exaggerated. Okay, these are very exaggerated pictures. If you look at the difference between a perfect circle and a ellipse, the difference is pretty small. They're very close to each other. Anyway, so two terms here are perihelion and aphelion. Perihelion is the point when Mars or any planet is closest to the sun. Aphelion is the point when it's furthest away. I will point out real fast, I think you'll see a picture that shows this in a second, but actually perihelion for Earth usually happens around January 2nd or 3rd. So that's interesting, right? Because you think perihelion, we're closest to the sun, it would be hotter and cooler when we're furthest away. But again, the amount, this picture is exaggerated. The amount that you're closer is about 5 million miles, or maybe it's 3 million miles, which is kind of a lot, but that's not really, it doesn't really have a big effect on the sun compared to how far the sun's heat compared to how far we are away. Okay, the second observation that Kepler found that's incredibly important here is that this planets changed speed as they went around the sun. So they moved the fastest when they were close. They moved really fast over here, and they moved really far away over here. And so it was really complicated because they would constantly change speed as they went around. But what he also found out that made things a little bit simpler is that the areas that were swept out by the planets were always the same in the same amount of time. So if this area here, this like kind of thick triangle and this little thin triangle, if they have the same area, they represent the same amount of time. Now this might represent just a month or whatever, but the point is it moves really fast over here, really slow over here, but the same amount of time occurs in each of those. This is called equal area and equal time a lot of times. So this is the second law of planetary motion. The line connecting the sun to a planet sweeps equal areas and equal times. So we move slower over here and moves faster over here, but it's always the same amount of area that gets used up. Now this is also important because when we think about comets, we're eventually going to talk about space rocks, but comets have highly eccentric orbits, right? They are, when we talk about these, they're very circular. I talk about planets being mostly circular. Again, this is an exaggeration. They're mostly circular, but not perfect circles, and that was the discrepancy. When we talk about comets, they're not close to perfectly circular. They're very elliptical orbits. And so comets don't stick around very long because they don't stick around the sun very long. They're moving in highly eccentric orbits. So again, think about the area as they move far away. The area there is going to be moving incredibly fast as it gets close. And this is why they don't stick around. And also why they don't come by very often, right? Once they go away, they might be gone for thousands of years before they come back. So then Kepler found there's a relationship between the time it took a planet to go around the sun and the average distance from the sun. So you see here that if they took and plotted the cube of the semi-major axis, that has to do with how far it is away, and the square of the orbital period, you get a perfect line. In fact, actually, this was one of the reasons why they were able to find out about the asteroid belt. Notice there's a gap here, right? There's this like perfect little, okay? But there's a gap in the middle. That's the asteroid belt. And again, this points out there's another place. This is a place where there's sort of this gravitational stability, that there should be something there. And sure enough, there is. Well, at least there was. And now it's just kind of broken bits or remnants of something that may have been there in the past. Now, obviously, they added other ones on. They didn't know about these, but they did know about these. And so it matched up really well. So you can take Kepler's third law and turn it into an equation. P squared equals R cubed, where P is the period in years, and R is the semi-major axis in AU. So let me talk about AU real fast. AU is simply an astronomical unit. For a long time, again, these people are very smart. They can use geometry and similar triangles and these sort of things. They can use this to figure out a lot of information about our solar system. But because they were using similar triangles, you may remember when you do similar triangles, it's about ratios, right? So it's like 2 to 5 or 1 to 6, okay? So there's one measurement they really can't get that they need. So what the astronomers did at the time was they just said, okay, well, we're going to find the distance from the sun, the average distance from the sun to the earth. We're going to call that 1. They call it 1 AU. And so that 1 AU, they didn't know what the answer was. So everything you're going to see is in terms of AU. Now today we know how big an AU is. And it's pretty limited, right? Because AU works well for our solar system, but even the nearest star to us is going to be several thousand AUs away. So it kind of limited, but that's why you see these things in AU. And you'll still see AU used today. So obviously planets like Jupiter, I think, I don't know. I'll probably get this wrong. Off memory, I think Jupiter's like 4 or 5 AU away versus things like Venus are going to be less than 1 AU away. Okay. You got this equation down because they're about to use it. P squared equals R cubed. If you have it up on your computer, it's fine. Otherwise, you might want to write it down. Okay, let's try it out. So we're going to use Kepler's third law. It says the comet's located 74 AU from the sun. Find the period in years of the asteroid. Okay, So if you're watching this video later, you can pause the video here and try it out. We're gonna pause our recording here and try it out, and I'll come back after we give you some time to practice. All right, we're gonna go over this one. I think people are a little lost. So the equation is just p squared equals r cubed. P is period, r is the distance. It says the comet's located 74 AU from the sun. Find the period in years. So we don't know what P is, but we do know what R is. R is 74 AU. So I'm going to write that out. Just let me get into my brush. P squared equals 74 cubed. Obviously, you'll need to use your calculator unless you happen to know what the cube of 74 is. And if you do, you probably should be at a different place because you're some sort of polymath. That's 405,224. So that's going to be equal to p squared. I would like to get p by itself. So what am I doing currently to p? Well, okay, but what am I doing with p right now? What is the mathematical operation I'm performing on p? There's this little 2 up here. What does that mean? You'll never seen a square before? Speaking a different language? Square? You know squares, right? Hopefully. Okay, it's squaring. Okay, so right now I'm squaring p. That's what I'm doing. So what is the opposite operation? What's the opposite of squaring? Square root. So all I need to do to get p by itself, take the square root of both sides. So the square root of p squared is just p. And the square root of this, again, I'll have to use my calculator, is 636 point, yeah. Because this is p, that's period, that's years. There you go. This comet, if it's 74 AU from the sun, which is a pretty good distance from the sun, that's fairly typical for comets, 636.57 years. So you can start to see why, comets come by. We can't always predict when a comet will come by. There are certain comets called short-term comets, like Halley's Comet, that we can predict, right? Comes by every like 78 years, 75 years, something like that. Yeah, we can predict because it comes by very frequently. Most comets coming by once every 1,000, couple hundred, couple thousand years. So again, that's why you can't necessarily predict when they come by. Okay, let's look at another practice. I want to come back to this one in a second. We'll do this one first. Calculate the period of Pluto, which is 39.5 AU from the sun. All right, so again, if you're watching the video, pause it here and try this on your own. Okay, hopefully this one was easy. I'll show you my solution. Okay, so again, p squared equals r cubed. P squared, we don't know the period, that's what we're looking for. So p squared equals 39.5 AU is the r there. So, sorry. Nope, I messed up. Let me redo it. The good thing we're looking at this. I just put in a 39.5, but that's what's supposed to get cubed. So this is not the right number, right? It should be 39.5 cubed. So 39.5 to the third. So I get p squared equals 61,629.9 or whatever. So then we take the square root of that. And I got 248.3 years. Sorry about that. Okay, I want to look at one where it's the other way around. So on your slides, it's back here. Here. Where would a planet need to be located so it would take 16 years to go around the sun? So let's say we have some planet where we can place the planet anywhere we'd like. We want it to have a period of 16 years. So this time, it's still the same equation, right? P squared equals r cubed. But this time we don't know r, we do know p. So this is a situation where we're trying to get r by itself. right, so here, write my equation first. Get my pen first, actually. All right, so we have p squared equals r cubed. This time we know p, we don't know r. So we'd have 16 squared equals r cubed. All right, so 16 squared is 256 equals r cubed. But how are we going to get r by itself? So once again, go to the same methodology. What am I doing to r right now? What operation is being done to r? What does this 3 here mean? Yeah, I'm multiplying myself 3 times, I'm cubing it. So the opposite of cube, you know what the opposite of a cube is? Cube root. So I need to take the cube root on both sides. So on your calculator, if you do the cube root, there's a couple ways you can do this, right? So if I take the cube root of both sides, so the cube root function looks like this. It looks like square root, but there's a 3 there. Let me take the cube root of both sides. There are a couple ways you can do that. You may have, I think I have one on my calculator. It says like X, and then it's got a little square root symbol. So to use that, I just hit I had 3, and then I hit that button, and it'll do a cube root. The same way you can do a 4th root or whatever. The easiest way to do it is this, though, right? Hopefully you remember taking the cube root is the same thing as raising something to the 1/3 power. Those are the same thing. So what I usually do is I would do 256 to the 1/3 power. Or you can use the cube root button, but you got to figure out where that is and how to do it. Or you can just raise to the 1/3 power. It's the same thing. So then 256 to the 1/3 power. I get 6.34, well, I guess 6.35 AU. So most of you are 16 or probably soon to be 16. So in this case, if you lived on a planet that was 6.35 AU away from the sun, you'd be 1 year old now. So happy birthday. There's one more point I want to make about this equation here. Okay, so the equation that you saw is written like this. P squared equals r cubed. Now, again, this is a perfectly fine way to write it. If you want to find it just in terms of one variable by itself, you can do that, right? Like if I wanted to get just p by itself over here, right? We talked about this earlier. Obviously, I'm squaring p right now. So if I want to get it by itself, I would take the square root of both sides. And I would get p by itself. And then you have this weird thing over here, square root of r cubed. But there's another way we can write that. Because remember, taking the square root is the same as raising something to the half power. So this is the same as r to the 3/2 power. So this is an equation you could, this isn't in the PowerPoint, you're more than welcome to write it down and use it. If you know period, or if you want to find the period, it's easy. Take r, which is the distance from the sun, raise it to the 3/2 power, you got your answer. Likewise, you could solve for r, right? So this is all solving for p here. If you want to solve for r, I'll just rewrite it. P squared equals r cubed. If I want to get r by itself, I got to take the cube root of both sides. So again, I would take the cube root, and I have a perfectly valid equation which says r is the cube root of p squared. Or, once again, that's the same as raising something to the 1/3 power. So if I have p to the second times p to the 1/3, I get p to the 2/3. So this is really r equals p to the 2/3. So that's another way you can write it and do it faster, right? Because now if I know this, right, and I go back to this other, the problem we just had, right? So the question was, how long would it take for the, where would a planet need to be? So it took 16 years. So when the period was 16 years, I'm going to find r, right? So I would just take, using this equation, I want to find r, I just take p to the 2/3. So if I take 16 to the 2/3 power, I get 6.35, which was the answer we just got. So again, that's a faster way to do it if you want to do it that way, as long as you can identify. So you have those two equations. P is r to the 3/2, or r is p to the 2/3 power. Okay, I want to do one more because I noticed I didn't do any with distances smaller than 1, but certainly you can have distances smaller than 1. So let's do one more. What would the period for a planet be if it is located 0.25 AU from the sun? Okay, I realized I paused my video. I'm not exactly sure where, but this is the practice problem, so you can pause it here if you need to look at it. I also want to point out, in case I had this paused when we did this, but you can derive two equations, right? So you can derive this equation, p equals r to the 3/2. All I did was take, obviously, the equation p squared equals r cubed, took the square root of both sides, so the square root of r cubed, or you can rewrite it as 3/2. And that's what I'm about to do, so you'll see that in a second. Likewise, if you solve for r here, you take the cube root of both sides, you end up with r equals the cube root of p squared, or you write that as a fraction, p to the 2/3 power. Okay, so here is the problem we just had. So this is for a distance smaller than 1. Again, this works for any distances. And here is the solution I have. So what would the period be? So again, I derived again, p equals r to the 3/2. So 0.25 is the period, or sorry, is the distance, that's r. So 0.25 to the 3/2 power is 0.125 years. If you want to know what that is in days, just take 0.125 times 365. And this is roughly, this is roughly 45.7 days to go around the sun. Okay, so those are Kepler's laws. Again, Kepler's third law is the only one that has an equation. But I want to point out one last thing I want to point out about Kepler's laws here is that there is not so Kepler obviously derived these laws, right? But he didn't know why. Like if you ask Johannes Kepler, okay, but why do these things move around in ellipses? He can't tell you the answer, right? He doesn't know. It's not until later that Isaac Newton is going to eventually answer this question, right? So again, if you ask Johannes Kepler, hey, why does this work, or why do they move like ellipses? He would say, I don't know. But then later, Isaac Newton is going to come along, develop a theory or a law of gravity, and that will fit perfectly with what Kepler found. So the answer to why they move around in ellipses is because of the gravitational attraction between the planet and the sun. But again, they're not going to know that for a while. And that's something that happens sometimes, right? There's some mathematical discovery that we don't know the answer to. We don't know why it's like that, or what makes it be like that until later. Okay.